Okay, so this is our first lesson, first unit. We're talking about momentum. Okay, and I'm going to begin actually by talking about the last line that I have on there. Momentum is actually what we just kind of witnessed to some degree in the demonstration I did, those pendulums that are still hanging there, right? But what's actually interesting is that they both had the same momentum because they both had the same mass. And in theory, they both should have had the same velocity still too. Momentum is like what you can read on that last slide there. It's kind of a hybrid between inertia and kinetic energy. Right? You guys remember what inertia is from Physics 20? You guys remember Newton's laws? Let's do a quick recap. Newton's first law is, which one is it again? Inertia, right? An object that's in motion stays in motion unless an unbalanced force acts upon it. Newton's second law, force is equal to mass times acceleration. Newton's third law, you don't remember? Yeah, it's the equal and opposite reaction, right? I call it the retaliation of the little brother, right? My brother punches me, I punch him back, right? Equal opposite reaction, right? Anyways, let's go back to Newton's first law, right? Inertia is that stuff that's in motion stays in motion, right? When I pull that pendulum back, what does it want to naturally do? Well, it wants to keep on its path, right? It keeps going. It doesn't just randomly stop. Okay. Well, what it ended up doing, though, is it kind of transferred its inertia, its momentum, to the little bottle that fell over, right? So there's the inertia part there. And then it's also like kinetic energy, though, too, right? Kinetic energy is the energy of something in motion. So momentum's kind of a hybrid of those there. I like to say that momentum is kind of like how much oomph something has. Like if I have to put this into like people words, that's a phrase you'll hear me say, people words. You know? Not like technical jargon, but like just dumb it down to like something that anyone can understand. If it has more oomph, it has a lot of momentum. Does that make sense? I'm going to skip ahead around in my notes a lot, okay? Like I do this a lot. That's why I want you to have your notes in front. I'm going to go find this photo right here if you don't mind. Here's a good example of how momentum works. Think about how much it would hurt if it hit you. Think about that for momentum. Would it hurt if a bowling ball hit you? Well, if the bowling ball was rolling relatively slow, maybe not, but like if it's going at, medium speed, yeah, that could leave a bruise on your shin, right? Or what if Mariano Rivera hits you with a fastball? I mean, the ball is smaller, but it's going pretty quickly, right? That's momentum, how much oomph something has. It's not really force, and it's not really kinetic energy, and it's not really inertia. It's actually its own thing on its own. And that's actually what we're going to talk about with those two pendulums there in a little bit. I'm going to come back to that, is that momentum actually helps us solve that problem. Because they both had the same velocity, they both came with the same energy, but yet one was clearly different. I'm going to go to this slide here before I go back. I mean, in theory, when things have large masses and large velocities, then you have even more momentum. I'm not even sure if this photo is real. It's probably photoshopped. But like if you got hit by a train and it's going fast and it has a huge mass, that's catastrophic, right? Whereas like if something is going with a little velocity and a little bit of mass, it's not going to hurt you at all. Right? Imagine that, I don't know, imagine that you're about to get hit by a wiffle ball or a baseball. Which one's going to hurt more? Well, the baseball, because it weighs more, right? Unless you could shoot the wiffle ball at like the speed of sound. That might hurt then. You get what I'm saying? Because I mean, really, that's like a paintball then, right? It's going a lot faster, right? Then it's going to leave a bruise. Paintballs don't weigh that much, right? So that's momentum. So if I can go back here, momentum is that hybrid. It's mass and velocity. And so if I can kind of skip to this picture slide here, you guys have probably seen one of these things before in your lives, right? Anybody know what this is called? You guys know what it is though, right? I hear it. It's called a Newton's cradle. Yeah, this is an excellent way to demonstrate something known as conservation of momentum or conservation of energy. Okay, because basically what you do, right, is you hit this ball right here, right? You lift it up, just like I kind of did with the pendulum, right? And it comes and it swings and it hits this guy, right? But here's what ends up happening. Momentum gets transferred. This guy has a mass and it has a velocity. And it transfers that momentum to this one, which transfers it to this one, to this one, to this one, and this guy gets kicked out, right? And then it goes all the way up, and then it comes back down, and it retransfers its momentum back the other way, right? And these are things that go tick, 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 right? Eventually they stop. Why do they stop? Well, they do lose momentum, that's true, but they're also losing one more thing. Energy, yeah, right? In what form? I was going to say sound and heat, probably. The two most likely amounts, right? Because it's not really losing its energy to, I mean, there's a minimal amount of friction there, I imagine, right? As each ball kind of clicks into each other, you probably lose a bit of energy in in potential like heat and friction. And it makes that clicking sound, right? That energy is being subtracted from your total every time. But it's pretty minimal, right? So that's why these things last for a long time. They're useful for showing kind of the idea of momentum and collisions. That's a lot of what we're going to talk about here is collisions and ideas. So here's our first formula, basically, then. If you want to calculate how much oomph something has, it's not force, by the way. It's related to force, and we're going to come back to that. But if you want to calculate how much impact it has, how much oomph, it's mass times velocity. What's the formula for force? You guys remember Newton's law? What's the formula for force? Mass times acceleration. There's a little bit of a difference here, hey? This is the mass times the speed it's coming at you with. But force is the mass times how much it's accelerating, right? Because let me give an example to you here. Imagine that I shot you with a paintball gun. How much force are you being hit with? Well, hang on a sec here. There's a mass to the paintball gun, but was the paintball accelerating? Actually, if anything, it's decelerating. You're telling me that when you get hit with a paintball gun, it's negative force? So that's where, when one of you guys mentioned force right off the bat, I mean, you're in the right ballpark, but it's different, right? Force is a mass times how fast something speeds up or slows down. Momentum, or oomph, or we have another word for it, by the way. I may as well use it for it right now. Oh, sheesh, I'm blanking on the name. Impulse, there we go. I'm blanking on it already. We give the name for this impulse. Okay, that's how much oomph it has. It's not force. But, I mean, don't you guys kind of intuitively kind of get this? There's a bit of a difference there? Okay. Now, a couple of things about it. It doesn't have a special unit. So you know how, like, this would be in kilograms, this will be in meters per second squared, and a force is in a Newton. We don't actually have, like, some sort of special fun unit for momentum. So you literally just have to leave it in kilogram meters per second. That's its units. A couple other things. It is not a scalar value, not scalar. Energy is scalar, but momentum is a vector, so we do have to consider the direction. It's actually a really easy formula to work with. I mean, I think that's why I like to start with this in Physics 20 or Physics 30, just to kind of rebuild your way back in, right? But I mean, literally, if you can multiply two numbers by each other, there you go, right? But it's changing the way you're thinking about things now, right? So here's the slides I already did. You can either have a high mass or a low velocity. You could have a high velocity, a low mass. You could even have both, right? One of the reasons why we're going to talk about this then is like practical applications to life. There's a lot, right? I mean, sports right off the bat is a great one. If you are, for example, into baseball, baseball right now is all about exit velocity as you hit the baseball, right? The guy swings the bat, cracks the bat at the baseball, and really the key to getting a base hit seems to be exit velocity off the bat, right? The pitcher pitches the ball in at, say, 95 miles per hour. If a baseball player can hit the ball back faster than it came in at, usually exit velocities of like 110 miles per hour result in like home runs and stuff like that, right? And so collisions and impact and stuff like that is a really applicable part to life, right? Here's another one right here. Anybody know what this runway lane is for? Yeah, but specifically why? Yeah, what if their brakes fail? What if it's icy, right? So, I mean, the basic concept here is, what if you're a big vehicle going down one of these big, like, mountain passes, right? And all of a sudden, your brakes fail, right? And you have no ability to change your velocity. Because, again, how do you change a velocity? Change in velocity is an acceleration. How do you get an acceleration? An external force. What if you have no ability to provide that external force and slow yourself down, right? Your momentum is getting bigger and bigger and bigger, right? You have a mass and you have a velocity that's going to increase, right? Well, that's what this little runway lane's for, right? So you end up trying to steer into that, hopefully, to slow yourself back down. Anyways, I'm getting off topic. Here's the second formula I need you guys to know. And this one's also, I gave you your formula sheets last day, right? Okay, so you'll see them on there as well. This is an interesting formula because I want you to focus on the units for a second here. Okay, I mentioned force earlier, and I'm going to come back to my pendulums now on this example here. We know that the formula for mass is in kilograms, and we know that the formula for velocity is meters per second. And that was equivalent to P, P being the unit for momentum. We just go with P. I actually have no idea why. It's probably Latin or something. But someone did point out, like, this is very similar to force. Okay? I want to talk about the units for force, if I can put them over here. If I can just do a bit of an aside, isn't a force equal to a mass times an acceleration? Newton's second law. Right? And so that means it's a Newton. But what is a Newton really made of? Well, a Newton is a mass, a kilogram, and an acceleration is a meter per second squared. Right? That's the unit for force. Aren't these two things almost equivalent to each other? Yeah, what's the one difference? This one has divided by time and extra time. It's divided by time and extra time. Does that make sense? There's an extra second on the bottom. And so we can actually make these things equivalent to each other if we multiply by an extra second. Because what that would do then is it would make the squared seconds cancel with this one right here, and now wouldn't these units here be equivalent to each other? And so this is the link we need to talk about now, because I want to come back to my experiment now here. The amount of force you have is actually based on how much time you have. How much time, now, when we're doing like the pendulum here, I'm not talking about how much time the actual like pendulum's in motion. We're talking about the amount of time that the collision takes place. Does that make sense? Like the actual impact amount of time. Let me give you a really good real world example. I'll come back here, I promise. Here's my picture. Here. Helmets. Why is there padding inside of helmets? Well, because it reduces the amount of force that occurs. But you know the way in which it reduces the amount of force is it changes the amount of time a collision takes place. Okay? By putting foam in there, it lengthens the collision. Let me give you some other examples like this. Airbags would be another one. Or any of you guys ever seen one of those like big whoopee cushion blobs that you might like jump onto in a lake? You know, like you jump onto the big cushion and it sends the person flying off the other side. You know what I'm talking about there, right? Why is that safe to jump into from like 30 feet above the ground? What's the amount of time the collision takes? Because what would happen if I were to take this equation right here and I were to rearrange it for force? So, can you guys follow? I'm going to divide both sides by time. See how that works? Well, hang on one second here. Doesn't this just prove what we already know? Isn't force equal to mass times acceleration? But what's acceleration? Velocity over time. Now, let's say you're having a collision, any sort of collision. You're crashing into something. Well, your mass is constant, right? Like, you weigh what you weigh. And your change in velocity is actually also constant. Because in a collision, you're going to go from traveling a speed to stopping, right? It's going to be 55 minus 0, or 20 minus 0, right? Because your final velocity is 0. The only one thing you can change is the amount of time something takes. If the collision takes a longer amount of time, imagine that I made this time value increase. How does that affect a fraction here? If the bottom of a fraction is bigger, what does it mean for the fraction itself? It's smaller. Do you guys know the word like reciprocals or like maybe an inverse relationship? Right? So if you can lengthen the amount of time something takes, it'll actually change how much force you have. There's actually a few variables in play for force. That's why I was hesitant to talk about force. Let's go back to our example now. So let's talk about the bouncy balls here. The one thing that's different between the two of them is how the bouncy ball reacted when it hit the container. Okay? I'm going to try showing you it one more time, and I need you to look really closely at what happens to the pink ball versus the duct tape one. Their masses are the same, by the way. What happened to the pink one here compared to this one here as it hit the collision? Watch one more time. They're both going to collide. Watch as they came back, right? Watch what happens when they come back again. Which one came back further? The pink one. Because what do bouncy balls do? They rebound, right? You know what ended up happening? It had an exit velocity. On this case right here, not only did it not hit, like it's not like it came up, it hit, and it stopped, right? It came up, it hit, and it bounced back, right? Throw anything at the wall. It bounced back off of it again, right? If I had two objects and I threw them both at the wall, it could hit the wall and kind of just fall off, or it could hit the wall and rebound back out. Does that make sense? And what I'm trying to demonstrate in this experiment right here is that actually what I did mess around with this time is the change in velocity. Because it went from having a positive velocity going this way. What happens when it comes back? What happens to its velocity? Now it's negative. The pink ball actually had a high, that's finally the way I wanted it to work. Does that make sense? The pink ball had a larger change in velocity. Right? They both went from, 15 to 0, but this one came back out at negative 14. And this one came back out at negative 3. See the difference there? And that actually can help explain what ended up happening. Because what ended up happening here is that this thing right here, your momentum change, you actually had more impulse. I'm not necessarily saying you had more force, because it depends on how much time there was. Because we actually need to like super slow motion zoom it down and figure out for like how many seconds that was in contact with each other. You know what I'm saying there? So these are the variables that we're working with here. Force, time.
Excuse the interruption. Can we have all the grade 10 learning S to K to the learning comments in their photo, please?
Just take these down because I'm done with them.
S to K to the learning comments. Thank you.
So I don't know. I hope I'm explaining this well here. These are the 4 variables we're working on when we're talking about collisions. Force and time, or mass and velocity. Right? So why don't I erase some stuff and we'll kind of talk about this one more time from the top here. What happens to the amount of force you have if you increase the amount of time? It would decrease, right? Airbags, safety cushions of some kind, right? If I were to jump off the roof of my house onto the ground versus jump off the roof of my house onto 3 mattresses stacked on top of each other, every 7-year-old boy who's ever tried that knows the mattresses are safer, right? But here's the theory why, right? If you can increase the amount of time, force must go down. Well, what we just witnessed is similar but different. Another thing that could happen is how much change in velocity you have. If something's coming in to collide and it bounces out like this, or it comes in to collide and it bounces out like that, which one has a greater change in velocity? Well, this one right here, right? Because it incurred more negative velocity on the way backwards. Right? And that's what we noticed with the bouncy ball. So now that I've kind of demonstrated some of these principles of like impact, or the word we use is impulse, let's try some examples. And there's really 2 ways I need you to know how to do this. Okay? The first is that if you ever need to find a change in momentum called impulse, you either solve for this side of the equation or this side. Either of these 2 halves of the equation will get you that impact amount. Okay? So if I give you masses and velocities, use those. If I give you forces and time, use those. The other possibility is you might just be asked to use this as a formula all on its own. Okay. Where like say I give you time, I give you mass, I give you velocity, and you just solve for the 4th variable. So now that we've kind of gone through the theory of this, let's try some examples. So we'll start basic. You guys have calculators? I have a calculator. 1,000-kilogram car goes 10 clicks. How much momentum does it have? 10 kilometers an hour isn't really all that fast. I mean, if someone were to throw a piece of paper at me at 10 kilometers an hour, I'm not really worried. Getting hit by a car, that's different. Why can't I just do 1,000 times 10? Why is this answer not 10,000? Yeah, we need the right units. So if I can write a couple of notes down here, momentum's units, which is capital P, is mass times your velocity. But the units are kilograms, meters per second. So we need to put it in kilograms and meters per second. So this one's good, but we got to convert 10 kilometers an hour to meters per second. Now, I'm going to show you guys the long way just in case it's been a while for you, and then I'm going to remind you of a shortcut if you've ever seen it. So here's how I like to show it. I would do this 10 kilometers per hour, and I would say that there are, like, say, 1,000 meters in a kilometer, and then, like, my kilometers could cancel. And then I could say that there are, in 1 hour, there is 3,600 seconds, and then this hours right here might cancel. I don't know if you guys have been shown how to do like unit canceling like this before. Is this maybe something you've seen? I do this in my chemistry class a lot. So if that makes sense to you, do 10 times 1,000 divided by 3,600. That'll give you, not your answer, but that'll give you your velocity in meters per second. Once you know what you're doing though, you just divide by 3.6. If anyone's never told you that. You either divide or times by 3.6. So 10 divided by 3.6 gives us 2.7 repeating. A couple of reminders here. I'm hoping you learned this. Always use all of the values you possibly can until you get to your final answer and then round. Because when I do this next little bit here where I'm going to do momentum is equal to mass times velocity, and I do 1,000 kilograms times 2.7 repeating meters per second. Don't just make it 2.7. Make sure you use like 2.7777. Do you guys know in your calculators how to like store numbers? Is that something you've been shown? I'm getting mostly nods. Does anybody not know and you're brave enough to kind of tell me? Should I do a tutorial on how to store a number? Sure. So I can get a calculator up here. So I'm assuming most of you guys have like one of these TI-80 something calculators here. Okay, so say you do some math, you do 85 divided by 900 and something. Sure, there's a number there. Completely irrational number, but you know you need to save all those digits. Okay. A good way to do this is to press STO, it's right above the on button, store. it's going to take your answer, it's going to put an arrow next to it. It's going to store it as any letter you want. So then go like alpha A, make it a letter A. And then from now on, if you want to do 8 times that number, just do 8 times the letter A, and now you're going to keep all your decimals. Has ever seen that before? Okay. Some calculators you can like go back up and like keep pressing the up button. So it's really important in physics. You don't want to make a rounding error. There's actually a really good historical story about how they missed Saturn with a rover because someone rounded wrong. It's serious. $1 billion satellite missed Saturn or something. Anyways, okay, so we're doing, what is that, 10,000 times by 2.7 repeating. So your final answer should be, ooh, I'm running out of room, sorry. I need to save my space better. 2777.7 repeating. You guys remember sig digs? Okay, so the way sig digs work, lowest number of digits that you were given as a value that you use in the question limits you. Because like, let's say I told you and this took 2 seconds. Well, 2 seconds is 1 sig dig, but did I actually use the number 2? No. Okay, so only use the numbers that you actually utilized, right? So this has 4 sig digs, this has 2 sig digs, so this needs to get rounded. So I'd prefer to see this then, 2.8, because we got to round it, times 10 to the 3 kilogram meter per second. You guys all familiar with the E being times 10 to the power of? If you want to, you can go like times 10 to the power of 3 if that way works. I find the E is just shorter because it's one letter. Do I need a direction? Normally we should, but the way I phrased this question, I just said the magnitude. So I mean, otherwise it's probably forward. Is that familiar-ish to you guys? Kind of hopping back into physics, some of those thoughts you need to have as you're answering a question. So if anywhere along the way here, like you're like, whoa, Chris, I have no idea what that letter E is. Can you talk to me later if you don't want to ask now? Like I'll answer now if you want, but imagine you're not going to want to. Okay, let's try another one. A 15-gram box gets slid across the table at a speed of 4.6 meters per second, and it slows down to 1.6 meters per second. What was the impulse imparted on it by the box? Imparted on the box. Something slowed it down. Probably friction, right? No, but how much oomph did it take away? I'm not asking how much force it removed or how much energy it removed. It's kind of a different way of thinking of it. How much momentum did it take away? Impulse, right? So if you want to calculate an impulse, it's equal to either F times change in T, or it's equal to M times change in V. Is it clear to you guys that we're using the second one of those two? Because that's what we have, right? So mass 15 grams. But wait, what's the standard unit in physics for mass? Kilograms. So hopefully you can do this, right? 0.015 kilograms, there's your mass. And then your change in velocity. This is kind of like the bouncy ball example. Sometimes things go from 5 to 0 or 2 to 0. They stop, right? But what if it doesn't stop? Or what if it rebounds? My baseball example is a good one, right? Think about how much force a baseball player is going to have to enact on a baseball for it to be coming in at 95 miles per hour and for him to reverse it at over 95 miles per hour. You get what I'm saying there? That's a lot of force that a baseball player requires to get it to go backwards. This one's not going backwards. It's just changing by 3.0 meters per second, right? 4.6 minus 1.6. So there's your mass times your velocity. Calculator. I got 0.045. Units are kilogram meters per second. Sig digs are good, so we could leave it that way. Because we only get 2, right? Or if you really wanted to, you could make it 4.5 times 10 to, what is that, minus 2 kilogram meters per second. So either of those would be acceptable. So that's how much, I don't know, impact oomph changed it. Again, it's not energy, and it's not force. But like, it's related though, isn't it? Questions so far? Okay. Let's try another one. A rifle leaves a bullet, or a bullet fires. A rifle fires a bullet. There we go. A bullet leaves a rifle with this speed, but now I'm going to throw in a new variable. Now I want to talk about how long it takes. Remember, that was the difference between force and oomph. There's a time factor, right? How much force would it require to make the bullet to leave in a small amount of time versus what if I could take 5 days for that bullet to leave? Right? Wouldn't that, I mean, that would be a sucky gun, obviously, right? But wouldn't that make a difference, right? You need a different amount of force to make things happen faster than slower. Right? So we are going to need to have, if it's happening in a short amount of time, how much, is it going to need a lot of force or a little force? If this happens in such a short amount of time, do we need lots of force or less force? Lots of force, right? What if I gave you more time? You need less force. Right? Let's think about this for a second. What if I wanted you to push something really heavy across the room? And I told you that you could have 5 days to do it or 3 seconds. Well, if it's going to take 3 seconds, you're going to need to use a lot of force. If I give you 5 days, you can do it little by little. You know what I'm saying? Right? So that's where this full formula comes in. That's the big formula. F delta T equals m delta V. And we know 3 of the 4 variables. Right? So I'm hoping you guys are fairly familiar with how to do a question like this. I like to rearrange if I possibly can first. So if I'm rearranging for force, I'm going to do this. Force is equal to m delta V divided by change in time. I hope I don't need to kind of go through the algebra of that. And then just plug in your numbers, right? So let's speed things up. This will be 0.00875 kilograms. Change in velocity was 225 meters per second because it probably started from rest. And our time was 3 times 10 to the minus 2 seconds. So here we go. I got 65, 625. Anybody else get this? Sorry, I always want to confirm with Clayton. Okay. That's still not right yet because I got to do a few more things in order to be like exact. First of all, my sig digs are wrong. I have way too much precision here. So it looks like I get 3 sig digs. So let's round it to 65.6. Unit of measurement for a force. And a force is actually a vector. So you should always consider this. Like, I'm not going to be mean like this on my tests or assignments, but you probably should be exact if you can. We should give a direction to this. For lack of a better word, why don't I just say forward? I'm assuming the bullet went forward. Otherwise, that gun's not working properly. So just make sure you're wary of what are vectors and what are scalars. So force, you care about direction. How's that? You guys can handle that? Cool. Okay, I got some more theory kind of to talk about here. So I've got some diagrams shown in here. And it's really the same thing that I was discussing before. It's the idea of how do you change something's impact, its impulse, its oomph, right? And I was going to bring in another demo, but I wasn't able to. We ran out of eggs last night, so I couldn't bring this one in. So, I mean, just imagine this scenario here, right? I'm going to drop an egg on concrete. I'm going to drop an egg on a bed of straw. Anybody play Assassin's Creed? Know the whole diving into the straw kind of thing he does, right? Well, why does that work? I mean, okay, that probably doesn't really work in real life, but why could that work, right? It's all about this concept here, right? If you have a short amount of time, it means from an inverse relationship, the amount of force goes up. And the force is what breaks the egg. But if you could lengthen the amount of time it takes, that would decrease the amount of force. Right? So it's the same sort of logic as with the, yeah, sorry, I should have moved that out of your way. It's the same sort of logic as with the cushioning inside the helmet, or cars are actually designed this way. I don't know if you guys are aware of this, but like cars back in the 70s and 80s were not very safe. Like I talked with my my grandparents. They didn't even have seat belts back then. They let all the kids just lay down on the back seat of the car while they drove in the middle of the night. You could like sleep laying down on the back seat. Those are like big boats of a cars, right? What we've now learned is that in order to make cars be safer, you have to have crumple zones. You guys ever heard of these? It's actually, it kind of sucks when you get an accident. I had a friend of mine, he got into like just the minorest of fender benders. But like the front end of his car got crushed like you see in this photo here, and he had to get a brand new car. Like it was a total write-off, right? But the whole point of it is that it helped keep him safe. Like he was very safe in the accident because what ends up happening is the front end of the car crumples. Just, I mean, imagine like a tin can being just like, I don't know, the smack it against your forehead kind of thing you might see, right? You've ever seen that, right? Crush a tin can, right? But the longer it takes for the compression, well, the more time, the less force, right? And so it helps keep us safe. It just means we go through cars more often. That's all, right? So in theory, all cars should kind of have a front end and a back end and maybe even sides that have that impact absorbing body. Right? So you guys all get that concept? Okay, we'll move on. Okay, let's try a couple of examples to illustrate this. Again, we're kind of doing the same formulas, so I'm sorry it's the same thing over and over. Here's your scenario. A 75 kilogram man is in a car accident and he's going from 65 to 0 because he hits a brick wall. I got to point something out, actually. It's probably worse than that, actually. Because it's probably not from 65 to 0. It's probably from 65 to negative 10. Because when you crash into something, you don't probably just come to a direct stop. You probably crash and ricochet. And didn't I already show you in this demonstration? The ricochet is actually worse. Why? It increases your change in velocity. And so now there's more change in speed. So it's actually better to actually come to an instant stop than it is to crash and go backwards. Does that make sense? So anyways, let's assume, though, that he comes to a complete stop. And this is the amount of time it takes. Let's do the math for how much force there is. You guys want to try this one without me? I've already done one like it, right? Take a stab at doing it without me, and then I'll throw the math up later. I'm going to grab a drink here. And if you really want to go ahead here, it's the exact same math for part B. The only thing that we're manipulating now is the amount of time. I mean, it didn't go from a big change, but what happens if we change the amount of time the collision occurs over? Right, so give it a try. See whether you beat me to it here. This is something I'll often do. I'll let you guys try it. So, I mean, if you want to watch, go ahead and watch. I'm just not going to narrate, if that makes sense. So try it on your own and then look up at me if you want. So if you do finish here, take a look and see, do you get what I got? Anybody else get that? Is that a question? Or? Oh. Can you guys do this? Like, call me over right now if you're struggling or something like that. Yeah. Yeah, good call. I kind of meant amount of force just to be the magnitude. So that's a good question. Actually, can I say that to everybody? What was your name again? Peyton. Peyton asked a great question. We should talk about the direction. Maybe if I just asked you for the magnitude, I guess we just need the numerical value. But which way is the force occurring? In the forward direction or in the reverse direction? In the reverse direction, isn't it? Because isn't it the wall? Like if I'm going this way, right? I got hit by the wall back the other way, right? So I guess in theory, right, the amount of force that I'm occurring is the other way, right? However, I got to point something out though. According to Newton's third law, there's an equal opposite reaction, right? Really, the wall hits me with that much force, and I hit the wall with that much force. So you know what I'm saying there? Like that really wasn't the point of the question, but I guess in theory, what is stopping you? A negative force of that much newtons is actually causing you to come to a stop, right? If forward is this way, then negative is kind of stopping you. Hope I didn't bust my microphone. So, okay, did that make sense to everybody? Anybody else want to pause? Yeah. Yeah, because you'd have to consider, I didn't mention this, but like change in v, right, is vf minus vi. So if it doesn't say anything else, like the exit velocity would be vf and initial, but like if it doesn't say otherwise, let's assume 0. That makes sense. But you guys get what I was going for with the bouncy balls though, right? Because of the fact that the one bouncy ball bounced off with such a ricochet, it actually gave it more change in velocity, right? Because it went from positive 30 to negative 30, as opposed from positive 30 to negative 10, right? The more ricochet you have, actually, the worse it is. Okay, another skill I need you guys to possess, especially as we get ready for a diploma, you are going to be given graphs. It's one of the expectations. So I need you guys to know a couple of things about how to interpret a graph in terms of finding whatever concept you're looking for. In general, I'm just going to actually make a new slide here if I could, and then I'll come back to this one. I'm just going to make a new page here. Let's say I gave you a graph. Okay. And the graph was about, let's say, distance and time. And I gave you a graph that looked something like this. Maybe you guys are familiar, but the slope of the graph would be your velocity. And here's the reason why. You guys did slope way back in like grade 10 math, right? Slope is equivalent to like your rise over your run. If you ever have two numbers that are divided by each other, like say distance divided by time, if there is a formula on your sheet where numbers are being divided, if you find the slope of that graph, that would be what this is equivalent to. That makes sense? That's one of the two options. But there are many formulas where you're not dividing things by each other, you're actually multiplying. As a different example, if I were to give you a graph here of something's mass times its acceleration, and I were to give you this shape right here, what significance would the slope have? None. Do you know a formula where m divided by a equals something? No. But what about if I change my perspective? What about mass times acceleration? Is there a formula for that? Yeah, that's force, right? So the way that works then is it's like a shape. Rather than it being the slope, you need to find the shape of what you're looking for. Let's say I told you that the mass was 10 here when the acceleration was 5 here. What you would do is you'd make a shape like this, a triangle, and you'd say, well, the shape is 1/2 of your base times your height because it's a triangle. Your base was 5, your height was 10, and that would actually calculate your force. We call that area under a graph. I don't know if you guys have come across that before. You should have, I think, in kinematics. That's what I want to talk about here. If I were to give you a graph of force and time, does force divided by time mean anything to you? If it does, that's your slope. Okay? So like force divided by time would be your slope if that's meaningful. But what about force times time? Does that mean anything? Yeah. Force times time is your change in momentum, which is known as your impulse. So if you wanted to figure out your impulse from a graph, you need to find this shaped area here. Okay? And it usually means it's one of two things. It's either a triangle or it is a rectangle or square. In theory, once you take calculus, you can actually learn how to do it even more exact. But you probably haven't taken calculus yet, so one day I'll show you that if you want. So let's try an example here. Let's say that there is a car accelerating from rest. Here's the mass of the car. I want to find the final velocity of the car. We actually have enough information to solve this, believe it or not. Close. You also have to divide by 2. And the reason why it's the shape right here, the shape happens to be a triangle here. We didn't have a consistent force. Otherwise, you're good. I'll take it from the top here, though. If you want to find the formula, it's normally like F delta T equals M delta V, right? And so I think what UV was going for here is that, well, let's just do force times time divided by mass and we're good to go. But hang on, was our force consistent over the whole time? That wasn't a consistent force. So I have to treat this a bit differently. I have to say that really this right here is equal to the shape I have. And the shape I have is 1/2 of base times height, which is 1/2 of 5.78. I'll use an X in between. Maybe that'll help. Times, what is that, 3012? That will be your impulse right here. So it's not just force times time, that's half of that. That is equivalent to your mass times your velocity. So to get your velocity, I mean, you were right about dividing by the mass. You just missed the 1/2 bit, right? So if this makes sense to you, give that a try. And see if you can solve for that velocity there. I got 3 sig digs, it looks like. I got 5.80 meters per second. I'm going to say forward. Anybody else get that? Yeah, fire away. The shape. Yeah. Because it wasn't a consistent force, right? So maybe it's more appropriate to consider that for this half of the graph right here and this half of the graph right here, what would your average force have been? Wouldn't it have been kind of in the middle? Right? Like for half of it, it was under your halfway point, and for half of it was over. So like we almost are finding like the average. Does that make sense? Right? Now the problem there arises, well, what happens if you have a graph where your force goes up and down and up and down and it's inconsistent? And that was actually a real flaw in trying to solve problems until, well, it was until Newton. When Newton discovered calculus, they were able to kind of solve this problem better, because we'd say, well, what if I push hard and then back and hard, you know, and in different increments? Then how could you figure that out? It's easy here because it's like the halfway point, right? Does that make sense? Yeah. Good point. So you know what I've actually calculated here is a change in velocity. However, well, no, the reason why that part works here is that it said it came from rest, right? So if your change in velocity was 580, but it started at 0, then it's 580, right? What if you initially started at 1? Then it would be 680. If you started at 2, it would be 780. You get what I'm saying there? So the only reason why it's the 1/2 is that this was not a consistent force. And so to calculate this side of the graph right here, we had to use the shape. Let's try another one here. A golfed, I have a typo obviously, hits a long drive, sending a golf ball due east according to the graph. Let's figure out the impulse and the velocity. This is our last one, right? Yeah, it's our last slide. Right, so can you guys see again here how, imagine on this graph right here, this is how much force, this is force over time that the golf ball is being hit, right? For the first little while, the golf ball wasn't even being touched, right? Then the golf ball begins to experience some force, right? I imagine that the driver that it's hit with is flexing even, right? You ever seen a slow motion shot of like the flex in something, right? And so the amount of force is peaking, right? And then the amount of force tapers back off. Because, I mean, what probably happened right here is like the ball is finally no longer in contact with the golf club, right? During the time that the golf club hits the ball, it's going to have like been over this distance, right? Right? And so, anyways, we have an inconsistent force again, right? It had a max force of 5,000 newtons, but like when it began and when it ended, it wasn't at 5,000 newtons. Right? So again, if I want to calculate the impulse for A, impulse is either m delta v or f delta t. But the problem is, did I have a consistent force? Well, no. So let's use a shape instead. The shape is 1/2 of base times a. So along the bottom here, how much time did this take? Yeah, 1.0, by the way, I think is what it would be, right? Because we have a precision to the nearest 1 decimal place, so we should maintain that. So I would say it should be 1/2 of 1.0 seconds multiplied by my height of 5,000 newtons. And so it throws it off a little bit because we're used to it not having this 1/2 here, right? I think a lot of you guys are thinking, well, why do I need the 1/2 right here? But does that make sense though? Is that this was just the max force. This was not a consistent force. And so that's where like the geometry kind of comes in and solves the problem. So this will then give me my impulse. So I think I can do this with a calculator. What's half of 5,000? 2,500. So we have an impulse of 2,500 Newton seconds, or it could also just be a kilogram meter per second. Both of those are actually considered to be equivalent. So is your impulse. Yeah. So really, impulse is the momentum in a way. Like change in momentum is an impulse. An impulse would be like, I throw something against the wall. The impulse would be the wall stopping the object's inertia. Does that make sense? Like an impulse is something that changes something's inertia. It either speeds it up or slows it down. Here, let me give you another analogy. Anybody play volleyball? Okay. Volleyball would be all about impulse. Okay. Like, for example, I throw the volleyball up in the air and I smack it with my hand. The smacking with my hand is an impulse. I have now changed its inertia. I've changed its momentum. It's now moving, right? Well, then somebody bumps it back up. We do a couple more bumps, and then I'm trying to spike it back, right? But they go up for a block, right? Well, the impulse could be stopping the ball or having it bounce back the other way, right? Or maybe the ball was already going this way, and someone tips it over the net and adds to its momentum. Does that make sense? So an impulse could be something that speeds it up. It could be that it slows it down. It could be stopping it. It could be sending it back the other direction, right? Which is really similar to when we talk about force. It's just the impulse is what we use to describe it. It's the amount of oomph that it has. Does that make sense? Yeah, so impulse is a vector, because we definitely care about direction. If I don't tell you otherwise, you'd go with forward, but this said east, by the way, like it's hidden in the blurb up there. So yeah, good call, actually, because I should have put a direction on there. This should be east, because I kind of hid that way up there. Well, now we know how much oomph the ball was given, right? Because it was at rest, and now it's added this much impulse. And then I can now say that that should now be equivalent, this 2,500 should be equivalent to its mass times its velocity. So I'm going to need to, let's see, how can I snag this onto a new page? What can I do? No, that's not going to work. Okay, I'll just have to use a new page here, I guess. So hopefully you can remember this here. It was 2,500 Newton seconds was my impulse, and that could also be my mass times my velocity. But since I know that my mass was, someone help me out because I'm on the previous slide. What was the mass again? So let's go with 0.0459 kilograms. If you divide this number here by 0.0459 kilograms, right? Let's say you don't like Newton seconds because that's not really a nice unit to work with. So let's use the other one. Let's use kilogram meters per second. Kilograms will cancel. You'll be left with meters per second. So 2,500 divided by 0.0459. I got 5.45. 45 E4 meters per second, and it was traveling east. Clearly that's not right in terms of a real world context, because there's no way someone hit a golf ball that fast. Right? Golf ball. Because we did 1 times 5,000 and cut it in half to get the impulse, and we divided by the mass here. Yeah, I bet you I have like a wrong value in there somewhere, because there's no way a ball is getting hit that fast. Like that's breaking. What's the speed of sound again? 330 meters per second. So that thing's going Mach something. So anyways, minus the fact that the numbers are clearly out of scale. Were you able to follow how to solve that though? Okay. So hopefully we've kind of learned a couple of things today then. Let me do a summary here. We've learned a new concept, which is it's a hybrid of what we've learned. It's like energy, it's like force, but it's not like either of them. It's momentum. It's how much oomph it has. I shouldn't say oomph. Really, the word we use is impulse, right? As I move or push something, it's not necessarily force, although force is implied. It's force times time. However much force I use times the time I do it over, that's how much impulse I give, right? If I push something for 1 second, or I push something for half a second, the smaller the amount of time would require the more force. Right? So we've also learned in these concepts like some theory stuff behind it. So if you increase the amount of time, you decrease force. That's one of the theories we hopefully learned. Also, I really hope my demo helped illustrate to you that change in velocity is also relevant. Because if it bounces backwards, that even provides more. Does that make sense? Okay. One more thing. Mass is not likely to change. Right? Like your mass is what it is. Is that our bell? No, just an announcement. Okay. I got time? Perfect. I was worried I mistimed it here.
Again, all grade 10s with the surnames L to R to the Learning Commons for their photos. Thank you.
We've also learned that, of the 4 variables we've given, force, time, mass, and velocity, chances are your mass is going to stay the same. That being said, that's actually not how things work in the real world. Because, what happens if I throw something against the wall and it breaks into pieces? How does that work? That is actually the subject of our next lesson. So we're going to talk about that tomorrow, where we talk about, well, what happens in these collisions as object A hits object B and they bounce off each other, right? We're actually going to do a demonstration and a lab where I've got a little mini pool table up there. And pool balls are an excellent example of this. As one hits the other and they glance and collide off each other, let's figure out where their trajectories go. Accident recreation by forensics police officers would actually utilize this, where they want to try to figure out, well, how fast was that vehicle traveling before it collided with the other vehicle? Does that make sense? So one of the things I really want to do, I have a video camera that I use that has a fairly high frame rate, and it shoots in 4K, it says. What we're going to do is we're going to take some videos of various different collisions. I've got the computer lab book, and we're actually going to track the objects as they move, like frame by frame by frame. Does that make sense? And hopefully we'll actually be able to see how momentum is changing over time. So, anyways, I got off track. What did we learn today? We talked about some theory, and I think we learned about really two formulas. The first one's real basic, P equals mv. You're not going to be asked a simple question like that, right? Like, the level of complexity will be higher. That's what I want to build you towards, but hopefully you can multiply two numbers by each other, right? The other possibility is I give you the F delta T equals M delta V formula, and that really has two implications. Either you take half of it and solve for an impulse, or you use 3 out of 4 variables, right? I give you 3, you solve for 4. Fair enough? So, okay, here's what we need to do now. I know I have a little bit of time left over. I'm going to talk about this a lot for our first little while. That's my learning cycle there, the whole buy-in, knowledge, application, feedback, completion. Okay. Now that I've shown you something, you guys need to practice this a little bit. You can't just like hear me talk to you and learn by osmosis. I really think you need to actually do something. So I want to show you our schedule for the next few days and a few things that you can work on. My philosophy as a teacher is to kind of give you a whole bunch of stuff all at once, and have you guys be able to figure out what you want to spend your time on. So let me go to my schedule here and we'll show you what we're up to. What do I get till 10:25? Perfect. I have a few minutes left. So you guys have been on my website a few times, hopefully. Okay. Tomorrow, well, let me just go there first. So click on here. Physics 30, momentum. Okay, so first day of school introductions. Today we did momentum and impulse. Tomorrow we're going to talk about collisions. Okay. On Monday, I have a workday scheduled. When I give work days, it's really just time for you to do the stuff that I'm going to ask you to work on. Okay, but there's another reason why. We have an assembly on Monday, and so no, the assembly's in the morning though. So I think we're probably going to be good. We'll have time to work on stuff during that time frame. Okay. On Tuesday, I want to do a lab tracking collisions, where we're going to use the slow motion video camera, make some collisions take place, videotape them, and try to on the computer frame by frame by frame plot the motion of them and see whether the momentum actually is working the way we expect it to. Wednesday we'll do some collision laws, and then I'm going to give you guys some more time just to work on generic stuff. The following week, Monday, is one of my favorite ones. I've made a duct tape cannon. What I'm going to do is from the ceiling in the hallway, I'm going to suspend a large piece of PVC pipe. One end is capped, and the other end I'm going to put in a wad of duct tape. There's a hole inside the cannon. I'm going to put in some methanol, which is explosive, and I'm going to light it. What it's going to do is it's like a potato gun. It's going to shoot the projectile out. And what we're going to do is we're going to do some math and some recordings based on the observations we make. And hopefully my video camera will even pick up, because what's going to happen, anybody ever shot a gun before? What happens when one object goes that way? Hopefully what we're going to see is the duct tape goes this way, and the pendulum swinging thing is actually going to swing back the other way. So. Anyways, here's what I want you guys to work on for any time you have today and kind of going forward. I have 2 assignments for you guys to do. Okay. You should do this on like loose leaf paper, I guess. I don't need you to physically print this off because most of my students will just do it off their phone, right? But like, let me show you a couple of the questions that we have so far, and maybe you can't answer them all just yet, but we'll get there. Here's a basic question. In an automobile collision, the severity of an injury to a driver can be reduced by an airbag. I'm going to give you a velocity. I'm going to give you a mass. I am going to give you a time. You tell me force. Can you do that based on what I showed you today? Or here's another one. I've got a mass. I've got a velocity. I have got a time. Here I just wanted to change momentum. What was not relevant in this question? Yeah. Because we just want to change momentum, right? So to calculate change momentum, mass and velocity should do. So anyways, here's what I recommend. Work on the assignments little by little. Whenever I give you work time, I really believe in that application phase. Okay? But here's the other part, though. I also want to give you feedback. Please ask me for help. I will sit down and work on this with you. Because this is really step one. We're going to do activities, we're going to do assignments, eventually we'll do a quiz, eventually a unit test, and we're eventually getting towards building you guys to that diploma exam. Okay, so I guess the advice I want to give here, please don't just like be like, okay, I'm good for the day, right? Like try questions 1 and 2. Try even question 3, right? But like work on it little by little. Does that make sense? So that's all I have for the day. So I guess when the bell goes, you guys can take off. But I guess my advice would be don't sit and do nothing, right? Be productive. Do it while it's fresh in your mind. Okay. And I guess one last thought. I will put that video on my website if you want to rewatch this. So it's 55 minutes.